In this series of lectures, we're going to focus on transition metals and coordination complexes that are formed by transition metals. And so to start off, I'd like to just share two of the things that I think are so fascinating about this subset of the periodic table. First of all, transition metals are extremely versatile. Um, if you take this same atom and put it in different environments, it'll do completely different chemistry sometimes and be different colors. You can also take two totally different atoms, put them in the exact same environment, and get totally different chemistry as well, which is really interesting. It makes transition metals feel tunable, which means that we can try to impose some sort of control over their environment to get some sort of desired outcome. Which is exciting as a chemist because it means that we can design using transition metals to accomplish the chemical transformations we're interested in. So here's an example of actually an environment for a metal, which is a heme or a porphyrin. Um, and we have a porphyrin compound or ligand system in hemoglobin, an enzyme that is in our blood. And it has an iron metal, a transition metal at the center. And that iron embedded in this porphyrin structure around it, this environment, is red in color, and it reversibly binds oxygen and transports it around the body. And then by contrast, we have then a non-transition metal in a porphyrin, the same exact environment, but this is a magnesium. And you'll see this is found in plant chlorophyll. The magnesium in the porphyrin will be green in color, and it'll actually mediate an entirely different um, set of chemical reactions. My favorite part about transition metals is that they're really pretty. They form these gorgeously colored complexes that we actually consider to be precious gemstones at times. So here are a couple examples, and um, I've got garnet, peridot, and turquoise to talk about, and the chemical formulas underneath them are usually the ones that are generically represented of these categories of gems. But looking at the garnet, which always has this structure of something like this, oops, sorry, this 3-to-2 ratio of two different metals, followed by silicon tetraoxide. This magnesium is oftentimes an iron molecule as well. And similar in peridot, this magnesium 2 silicate is one form of it, but it is also often an iron atom as well, an iron plus 2 in both of these cases. And when we see these bright red colors, we see them for garnet, both if there's magnesium or if there's iron plus 2. And same with peridot, we see that yellowish color when we have an iron plus 2 or magnesium in that structure. And in these cases, that bright color when the iron is in place there is coming from those d orbitals of the iron plus 2. And it's really interesting to me that you can have the same ion, they're both an iron plus 2, producing such different colors to our eye. And that's because they're in different environments. And so that environment's really tuning the chemistry of the iron, but also just the visual beauty of the iron atom in that structure. Now, turquoise, here's the other one of the generic formulas for turquoise with this -2 charge. It's usually paired actually with a copper plus 2. And that copper plus 2 atom will give off this turquoise color, this blue-green color that's actually characteristic of the energy gaps in between its d orbitals. And that's where a lot of that color is coming from within the gem or the stone. And so again, the cool thing about this is that there's this wide range of chemistry, there's this wide range of colors, and they all seem tunable such that we could kind of impose our will on the chemistry of these atoms, which is exciting. So in this chapter, in this section of the course, we're going to dive into transition metals. We're going to think about them as ionic complexes and covalent compounds and coordinate covalent compounds. As we go through different examples.